Okay, I got it.
Yes.
I'm going to take you folks and put you over on my other monitor. Okay, so thumbs up if you can see my, you can see the slide deck. Thanks. Okay, that's great. Here we go. I'm going to keep it this size just for navigational purposes. It's problematic, I think, with Zoom to do things in presentation mode. At least for me it is. So anyway, we're going to rocket through the parts that we've already talked about. But the really cool thing, you know, as we're in younger grades, our younger people love magnets because they offer a force at a distance, and it seems almost like magic. But really quickly, we recognize how intertwined magnetism and electricity are. And they're really sort of part of the same thing. So we talked about this idea about north and south poles, but the north and south poles for a magnet can't live individually. They work together. So field lines go from north to south on the outside, but then inside they go from south to north, because magnetic fields are actually continuous. And we talked about the importance of the Earth's magnetic field in protecting us from solar wind and ways to manipulate the magnetic fields to be uniform. But here's where things started getting really interesting. So this connection between electricity and magnetism, they always exist together. They can't exist separately. The permanent magnets that you might have played with as a child, you didn't plug them in, so it didn't seem like they had anything to do with electricity. But we are going to come back and talk about permanent magnets right at the very end. And then how you can magnetize things, which I think you'll find fun. So you should be a magnet collector. So not hoarder, but collector. So when you see cool magnets, you should definitely, grab them. They're fun to have around. All right, well, here's right-hand rule number 1, where we use our thumb to point along the direction of current flow, and then our fingers wrap in the direction of the magnetic field. A coil is a way of enhancing a magnetic field. And then if you have a current carrying wire in a magnetic field, since the wire has a magnetic field, if you put it in an external field, they'll interact. And right-hand rule number 2 tells us the direction of that force. But this is the same thing as a free charge, like what we were just doing. So you don't have to be a charge that's trapped in a wire in order for this effect to demonstrate itself. And we also remarked about how a charged particle is going to show circular motion when it's in a magnetic field. This actually is the cause for the northern lights, or the southern lights too, if you've been down below the equator. So any particle that's moving in a circle is accelerating, and accelerated charged particles are going to give off light. So when our Earth's magnetic field causes deflection of cosmic rays, it causes them to accelerate, and they sort of bottlenose their way into the Earth's magnetic field. And in the process of doing so, they shed light. But also, this is used frequently, this idea that charged particles moving in a magnetic field feel a force that's perpendicular to their velocity, and therefore they execute a circle. This is also used in many different applications. So if you've heard of the word cyclotron, that's what this is based on. And here's some right-hand rules. Now, maybe if you've gained a little bit of confidence, you don't need the paper box anymore. You might be able to just do it with your right hand, and that would be great. But here's the new stuff. So calculating the magnetic field caused by a current carrying wire. So in the first slide, we used the right-hand rule to look at direction. And now we're trying to take a look at how that intensity changes as you get further away from the wire. So in this formula, I stands for current. And of course, we have 2 pi. Those are their usual values. and R, where R is the distance away from the wire. So this is an inverse law, not inverse squared, but just inverse. And so if you get twice as far away from the wire, then the magnetic field strength is going to go down by half. Now, a constant up front that is going to make our units work and give us Teslas. Do you remember epsilon naught? I was making fun of that before, called the permittivity of free space. Well, this is the permeability of free space, honestly. I wish they had names like, you know, SpongeBob and Patrick. That would be more interesting than permittivity and permeability, but that's okay. So roughly speaking, what this constant means is it's how fast a magnetic field can be established in space. And it's a pretty small number, so it doesn't take very much time. And I mentioned before that those two constants actually combine together to tell us what the speed of light is. It's really quite amazing. So 4 pi times 10 to the minus 7. We're going to do some practice problems here in a few, and we'll need that. So I'm just going to jot down a reminder to myself. Yeah, and it really is pi too. All right, well, if one wire creates a magnetic field and you place it next to another wire that makes its magnetic field, then we're going to get a force. So we know the force on a current carrying wire is going to be the current times the length of the wire that's in the magnetic field times the magnetic field strength times sine of the angle. So if we take that force equation and substitute in the magnetic field strength for one of the i's, then we wind up getting a general equation for what that force is going to be. Now, as far as the direction of the force, they could repel each other, they could attract each other. So it turns out it's parallel wires that attract each other. They're trying to suck them into each other to become one. And anti-parallel wires that really don't want to have anything to do with each other. We had mentioned before that a loop is a way of enhancing the magnetic field strength. So a solenoid is a way of intensifying the magnetic field strength. And it's an interesting phenomenon that when we intensify the magnetic field and we're pumping some current in, that magnetic field is actually hard to turn off. So that when you interrupt the current flow, the magnetic field lingers a little bit. It's really kind of interesting, almost like space itself has been magnetized. And you might think that this is kind of a rare phenomenon, but I'm going to just show you one really quick. And in order to do that, I'm going to stop share and should go back to my document camera. But I'm going to grab my document camera really quick and just to show you something. So well, I'm going to change my video so it's me. Put the light on. There we go. I'm going to grab my document camera. It's way up there. And this thing right here, I'm trying to put it in a place where you can see it well. Yeah, this is the cable. Hello, Magnet. What are you doing there? Just hanging out. Right. What I'm talking about is this right here, this clunky thing, right? What's the deal with that? Here's a USB cable. And there's like, why? Why isn't it just a straight USB cable? Right? You don't have this on your phone charging cord, right? But why is it on this document camera? This is actually a solenoid. And it's used in what's called a radio frequency choke. So it cuts down on interference on this USB cable because right now the document camera is trying to send a very complicated video signal along this USB cable. And so this choke coil is going to take out any interference. So it's useful. It's called a choke coil because it chokes out the high frequency stuff. All right. So anyway, magnetism is definitely all around you. It's not an odd thing. It actually happens all the time. So let's go ahead and take a look at some practice problems. And I'll switch back to the webcam, to the document camera. Probably have to reposition it. There we go, turn the light off. Ignore business. So I'm not sure if you have our agenda up or not, but I'll try and put down enough details so you can get a sense of what we're asking. A jumper cable, of course. That's a lot of current. So 65 amps. That's a lot. So if you are looking for jumper cables, if you think you're going to need them, this is not a place to go skimpy, because there's a whole lot of current that needs to go through there. So you want to buy nice, thick jumper cables. And they last a long time if you keep them in a safe place in your car. But it's nice to always have it around it. I'm one of those guys where, hey, has anybody got jumper cable? That's me. And let me tell you about the gauge thickness of these jumper cables. All right, so we're going to start this vehicle. How strong is the magnetic field 6 centimeters away from it? Find B when R is equal to 6 centimeters. So we'll draw this jumper cable as a big pipe. And at a distance of 6 centimeters, we want to know what is the strength of the magnetic field. Let's take this opportunity to think about which direction the magnetic field would be. If our current is going this way, right, which way would the magnetic field be? Down here. So 6 centimeters away. Well, you point your thumb along the direction of the current flow, and then imagine your fingers coming up and wrapping around this like you're going to hold on to this wire and hang from it. So you can see that once I wrap my fingers all the way around, down here the magnetic field is actually into the page. And then above the wire, my hand would be like this. So the magnetic field is coming out of the page. Okay, well, let's go ahead and calculate it. So we have this U0 thing, and it's directly proportional to the current flow and indirectly proportional to the distance. All right, looking good. So now let's go ahead and put in the values. So mu0 is 4 pi times 10 to the minus 7. Over 2 pi, so pi's cancel. And then I is 65. sorry, it's not F, it's supposed to be B. And times I is 65, divided by 6 centimeters, but we need to convert that into meters, so it's 0.06. So as I mentioned before, we've got a little cancellation here. So the pi's will cancel, and a factor of 2 will cancel, so I've got this. And here's how you would type it into your calculator. So you would write 2e minus 7 for this part times 65 divided by 0.06. I know you already know how to do this. And why don't you go ahead and type the answer into the chat. It's not a lot. It's not a very big number. You just use 2 significant digits. Did you get something that looks like this? Yeah, that sounds about right. So this is on 10 to the minus 7. This is on the order of about 10. So we've got 10 to the minus 6 so far. And down here we have 10 to the minus 2. Right, so 10 to the minus 6 divided by 10 to the minus 2, 10 to the minus 4. So that sounds about right. Good. Any questions about that? Okay, I'm going to hop over the next question and do, because it involves a drawing. So I can do that with the document camera. I'll do that right at the end. So let's take a look at 28. Now we have the force between 2 parallel wires. So one of the things we want to pay attention to is what's the direction of the current flow. Are they similar or are they not similar? So we have 2 pipes that are next to each other. And they're 35 meters long and 6 centimeters apart, and each one carries 25 amps in the same direction. So 6 centimeters apart, 0.0, oops. Meters. Okay. And we want to find the force between them. So it's a little complicated. We're just subbing in from one equation in for the other. But so we're going to have mu0, of course, over 2 pi, and then the 2 currents. So I1 and I2 divided by R, and then times their length. So you might ask, are they all going to be the same length always? Well, they don't have to be, but the L we're referring to is the length that they have in common. So if these wires, I mean, we had to get the current in here somewhere. So if these wires actually went their separate ways like this, we're really just referring to the length that they have in common. And so L was 35 meters. Okay, great. Well, here we go. So mu zero is 4 pi times 10 to the minus 7. So you might be thinking, you know, if this is always 4 pi times 10, why don't we just call it 4 pi times 10 to the minus 7? Why don't we stick that there instead? And the answer to that question is because, again, this is used with a permittivity free space to find the speed of light. So that's why it's got significance. So 25 a couple of times divided by 0.06. This is a very small number, so it's hard to actually get a significant force like this. And then this is 35. So let's see how we're doing. This is on the order of 10 to the minus 2. It's on the order of 10, on the order of 10, on the order of 10. So far I've got 3 powers of 10 in the numerator, and then 10 to the minus 2. So that's 10 to the positive 5th, and then 10 to the minus 7. So I'm expecting an answer on the order of 10 to the minus 2. And we have some cancellation, of course. So 2 pi is going to cancel. This will leave us with 2. And I suppose I could like cancel the 2 and make this 0.03, but that's splitting hairs. And that's in newtons, of course. All right, thoughts, questions? Okay, well, that sounds good. So we'll shift gears here. And take a look at the rest of the chapter.
How do we determine the direction of the force?
Okay, great. Well, we didn't do an example with a solenoid, but that's okay. By the way, these are 2 parallel wires, so they'd be attractive. Right, so solenoids and electromagnets. Anytime, like just picture, you go up to the car door and you hit the keyless entry remote and it goes control. That was a relay. That was some kind of solenoid letting go. So electromagnetic locks are very, very common. In this case, we have 120 volts AC. And so when you close the switch, alternating current is going to flow back and forth in this coil, and it's going to suck this little spring in to hit the bell and go back out again. So Ampere's law, we're not really going to talk too much about. But torque, for sure. Yeah, so here's the idea. We have one of our, like an old analog meter. And so wire goes in, goes around some kind of iron core, and then comes back out again. And so if this is set on a nice little pivot, then if this loop, even though it's square, we still call it a loop, if current's flowing through it, then it's going to set up a magnetic field inside the loop. And that's going to try and align with this external magnetic field. Or another way to think about it is that because charges are flowing, they're going to feel a force. And the charges are flowing in the opposite direction here, so they feel a force in the opposite direction. So these two forces, even though they're equal and opposite, since they don't originate at the same point, they wind up twisting the wire. And the spring is here because if we didn't have the spring there, then this would just twist and it would be all done. But since the spring resists the torque, it rotates by an angle that's proportional to how much torque, and then that gives us an idea about how much current's in there. The motor effect, of course. Well, just like what we saw in the previous slide, that if there was no spring, then what would happen is that this coil would just align itself with the external magnetic field, and that would be it. Right? So what makes the motor a little bit different is that we trick the motor. So we have a wire that goes in and then wraps around this thing that gives the coil a chance to hold its shape. And there's actually probably in practice hundreds of windings of wire around here. And then we have two external wires that come in to make contact with the wires that are permanently fixed to this armature. So as the motor spins around, the alignment of their contacts changes. And so just as the motor is trying to align itself with this external field, then they're going to switch. So that's what happens with these contacts, is that the wires that come in make contact, but then the contact is switched. You can see there's a little gap in there. The contact is switched right at the last moment. So now angular momentum will have the armature continue to rotate, and then current starts going in the opposite direction, and now the armature wants to line itself up with the north pole. So these things, these wires that come in are called brushes. And brushes are necessary for electric motors, but in recent years we've had the invention of the brushless motor. And the brushless motor is really interesting because instead of having a coiled wire on the inside of a magnet, the brushless motor has a magnet that's surrounded by coils. And they can spin at very, very high speeds. But the downside is that the electronics needs to be really smart. And so that was the delay in inventing brushless motors, is that we need to have electronics that was smart enough and fast enough to be able to change, to fire off those coils. And I should try and find a brushless. Anyway, the bottom line is, if you see brushless motor, it usually means that the motors are going to go really, really fast, and will probably outperform everything. So I have if you're shopping for, presents this year, it's holiday season, if you know anybody who likes tools, if it's motorized, make sure it's a brushless motor. So I have a brushless cordless drill that's incredible. I have an electric lawnmower that's brushless, and that thing is crazy good. Okay, what else? What else runs on magnets? Speakers. So we have wires that are coming from our stereo, and they wrap in a coil. And they wrap in a coil around parts that are connected to this paper cone. So we know that sound waves is made up of vibrations, compressional vibrations. And so if the current in the wires is in sync with the music that you're listening to, then this paper cone is going to vibrate with a frequency in sync with the music that you're listening to. And then the idea about domains. So now we've actually have a chance to talk about what makes a permanent magnet. And so I'm going to alternate back and forth. And I'm actually going to do a little experiment here. So since I know you probably want to know how to permanently magnetize something. I just have to get a couple of props. So the basic idea, what's the connection? If we know that currents create magnetic fields, then what makes a permanent magnet? What's that all about? So we can think about electrons in orbit around their nuclei. And since they are charges that are moving in circles, they're going to create magnetic fields. But for most materials, those electrons are fairly random. And so they don't really contribute very much. Now with some metals, iron in particular, it's possible for some of the conduction electrons to wind up sort of kind of riffing off each other and starting to pick up the magnetic orientation of their neighbors. So in particular, if you take a permanent magnet and you touch a piece of iron like a paperclip, then that's going to make that paperclip into a magnet. I don't have any paperclips here, but I do have a couple of small bolts. So I'm going to get my props out here just to take a look at that. And then I'm also going to get a couple of really tiny bolts. I'll just get one because these are easy to lose. Okay, good. Well, I'm going to, sorry, hold on. So let me give you the hand waving explanation first, and then we'll take a look at it in real life. So these arrows are designed to represent clusters of conduction electrons that are kind of in agreement with each other. And those are called domains. Usually these domains are kind of random. So that means that the metal itself is not going to behave like a magnet. However, if you can get them to line up, then it does behave like a magnet. So if we could just keep that image in mind, I'm going to stop sharing and then take a look at the document camera. And the document camera is going to take a wild ride down to my desk. So hang on. Whoa! No. Okay, I've got a couple of bolts here. I'm going to zoom out a little bit. All right, here's a case for my bolts. These are M3s, metric 3 millimeter. And here's my horseshoe magnet. Okay, so again, to illustrate that point, if I put one of these bolts, so my magnet is holding onto it, I think you're still upside down. Okay, that's better. At least for me, it's better. And so here's one of these bolts, and if I bring the bolt nearby, then I can pick it up. So this little bolt is, because it's connected to the magnet, is also acting like a magnet. The magnet's acting a little tired tonight. Right. Let's do that one more time. Slow motion. So here's my bolt connected to a magnet. I bring another bolt nearby, and right now this is not acting like it's behaving like a magnet. But once it's in contact with the other bolt, it too starts like acting like a magnet. So initially the domains are randomly oriented, but when they're in presence of an external field, then they line up, and that's how come they act like a magnet. And then they cause the domains in this to line up as well. So my problem the other day, I think I had mentioned this, is I was working on some tiny robots and I had tiny bolts. So there you go, that's a tiny bolt. Tiny bolts require tiny screwdrivers, like this. I'm going to zoom out for this. And so my question is, how do I magnetize this? And the answer is that those magnetic domains, if they linger for a little while, you can always shake them up by just banging them, or also you could just apply heat. So here's a candle. It's almost burnt out, but you get the idea. So in order to magnetize this screwdriver, I would let it touch the magnetic field, and then I would heat it up. Now, as I heat it up in the candle, the magnetic domains get randomly dissociated, but then I take it out of the fire and I let it cool off in the presence of the magnetic field. And as it cools off, those domains that start, the electrons start slowing down a little bit, and then those domains start coming together because they're in the presence of a magnetic field. I don't know if it is still magnetized at all. I might have to charge it up again. But essentially, that's the idea. So you heat up the piece of metal, a screwdriver or something else you want to magnetize. You want to have a pretty strong magnet nearby. So you heat it up, and then you allow it to cool in the presence of a magnetic field. And then that's going to permanently magnetize this. Permanent, of course, is a relative word, because if I bang it a few times or connect it to a magnet in the wrong direction, which is, I think, what happened, then that collective magnetism is going to decrease. But there you have it. That's how you magnetize something permanently. All right, I'm going to switch cameras and just see if you have any other questions. Hi. Right, so I think that does a pretty fair job of covering the beginning part of magnetism. So just like in other fields, we're taking a look at steady state magnetism. When I see you on Tuesday, we're going to look at changes in the magnetic field. What happens when the electric field and the magnetic field become dynamic. So that's the plan. So feel free to let me know if you have questions. You can stick around on this Zoom meeting if you have anything that you want to talk about. But otherwise, have a nice weekend. Enjoy the snow on the ground tomorrow morning. They're skiing at Killington.